differential equations can be difficult things to solve. It can be difficult to find our solutions. So sometimes we'll resort to graphical methods. And in this particular video, we'll talk about direction fields, which is a graphical method for finding or getting a sense as to what a solution to a differential equation will look like. Okay, so suppose that our differential equation is of the form where the derivative is some function of x and y. So we can explicitly solve for the derivative, and it's what's called a first order derivative because it only involves dy dx. It doesn't involve the second, third, or higher order derivatives. So if dy dx is written in terms of x and y, at any particular point, we can compute the derivative. We can find the derivative by substituting the x and y values in for the x and y in the expression. Derivatives measure slope, so we can draw a small line at that particular point with the given slope. So here's an example. Dy dx is the difference of x and y, x minus y. What that means is at any particular point, we take the x value and we subtract the y value. So here we have the point 1 comma or negative 1 comma 2. So it's this point right here. At negative 1 comma 2, when x is negative 1 and y is 2, we get a slope of negative 3. So it's hard to see, but I've just drawn a small little dash here with slope equal to negative 3. And you can see it kind of aiming for this point down here, down 3 over 1. Okay? What we can do is we can enlist the help of a computer to draw many of these types of slopes. And if I do this all over for this particular function, this is the graph that I end up with. Once again, right around negative 1 comma 2, we have a little dash with a slope of about negative 3. Computers are particularly helpful for this. If we know a single point in one of these direction fields, we can almost always draw a graph. So what I've got here is and the graph is already drawn for us, but we'll go ahead and trace it. Remember we had the point negative 1 comma 2. So it's kind of hard to see in there, but there is the point negative 1 comma 2. Okay? When I draw a particular solution for this, what I want to do is I want to draw the curve so that it follows those slopes. So right now the slope should be negative, and as I move towards the right, I can see that those slopes are starting to kind of taper off. They're not quite as steep as they once were. And down here you can see we're tracing these little slopes right along the curve, and we end up with that particular solution. Okay, so you can picture them pretty well. I like to imagine that this graph represents the current in some sort of body of water. The point that we pick is like a cork that we drop down, and then we just watch its path as it follows those little dashes. If you really want to, I used a computer algebra system to figure out what the exact solution was. It is y equals 4x e to the negative x minus 1 plus x minus 1. If you want to, find the derivative of this creature, substitute it into the left side, take x minus this function, and you should get the same expression. Let's go ahead and do the same thing we were doing here. Let's draw the particular solution when y of negative 2 is equal to 0. What this corresponds to is it's the particular solution that contains the point negative 2 comma 0. So we go over to negative 2, 0. There it is. And we follow the little dashes. Well, again, the dashes are kind of sloped negatively, so it's going to go up something like that. As we move towards the right, once again, they get less steep. And it seems like it's going to start approaching that other function there as well. Okay, let's look at part B. Draw the particular solution where y of 1 is negative 2. Again, the 1 is the x value, the 2 is the y value, negative 2, excuse me. So we go 1, negative 2, we're down here. Now at this point, the slopes are positive. So as we move towards the right, we should actually be going up, And they actually start to get a little bit less steep, but it looks something like that. So that's the particular solution that contains the point 1, negative 2. So we've got parts A and parts B taken care of. Now it's time for part C. Not done with it yet, but there's one particular solution that is a line. So what we want to do is we want to imagine that we can drop a cork somewhere in this body of water, if we want to think of it that way, where when I drop it, it will follow a line. Well, I can see that's certainly not in this region up here. This region, they all move like that. And in fact, it looks like most of the solutions up here, maybe all of them, will have that sort of bend to them. Down here, they move up in this fashion, but I see as I get closer over here, oh, okay, I can kind of see the little dashes that are all on a straight line, and they're right around here. Okay, so that looks like the particular solution that's a straight line. Now I'm actually going to kind of reason through why this makes sense. What is the slope of that line? Well, the slope of that line, let's see, if I pick any point, here's a point, I go up 1 and over 1. Oh, up 1 and over 1, it looks like the slope of that particular point is 1. Wait, slope is the derivative, dy dx. But wait, dy dx is x minus y. So that must mean that x minus y is equal to 1. X minus y equals 1. If I subtract x from both sides, I get y equals negative 1. I'm sorry, not negative 1, just 1 minus x. And if I multiply both sides by negative 1, I'll get y equals x minus 1. It is a line, as we suspected, right? It's a linear function. The slope of this line is, as we suspect, it's equal to 1. And the y-intercept is negative 1. Look at that. We got it exactly. Okay, so let's look at the final example here. An equilibrium solution is, remember, a solution where the y value stays constant. Okay, so that's what an equilibrium solution is. It's where the y value stays constant. Okay, so that would mean when I plop my cork down, it's going to move left and right. Well, I think we can see if I plop it down here, it's going to go down. That doesn't work. If I plop it here, it's going to go down. That doesn't work. No matter where I place it, it seems like it's going to go down. Oh, there's a place where it's kind of flat. Oh, but if I move it over here, then there are places where it's going down. So there are no equilibrium solutions, sadly. All right. So we're going to be charged with the task of sketching the direction field for y prime equals x squared plus y. And once we're done, we're going to add the particular solution when y of 0 equals 0. This is a little bit tedious. I'm not going to draw a lot of the graph. The issue with these things when we draw them by hand is that eventually, not in all cases, but in many cases, the slopes get so large that drawing a vertical line is just as convincing as drawing a line that's just shy of vertical. So a slope of 5 may be so large that it really looks more like a little vertical dash. All right, in these particular cases, I like to analyze the function, the differential equation that I'm given, and use that to make some decisions about how I proceed from here. For instance, I see x squared and y. X squared is more complex, not by much, but it's a little bit more complex. So what I'm going to do is I'm going to fix x values. I'm going to pick particular x values and then use those accompanied with the corresponding y values to find the slopes. I'm not drawing the graph very large. I'm doing it from -2 to 2 in each direction. So let's start off with x equals 0. When x is equal to 0, then we'll get y prime is equal to y, which means the slope at any given point is the same as the y value at that point. So let's see here. When y is equal to 1, remember x is 0, when y is 1, the derivative will be 1, which means the slope is 1. So it's going to look something like that. And what I'm doing is I'm kind of aiming back at this point, because that would be down 1 and over 1. The slope is 1. When y is 2, the slope, y prime would be y. Y is 2, so y prime is 2 as well. Again, that's kind of interesting. The slope is 2. I would go down 2 and over 1. So I'm still aiming at that point. Maybe we can make some conclusions about this. When y is 0, well, it's going to be a flat line, which again is pointing to that. Now let's just make a guess. If I'm down here at y equals -1, am I still aiming at that point? The slope is -1. I sure am. And when y is -2, the derivative is -2, which means we will go up 2 and left 1. So it's going to look something like that. We could fill in more, but this will give us enough of a picture here. Let's look to see what happens when x is 1. Now I'm going to take a bonus here. If x is positive or -1, then y prime is plus or minus 1 squared plus y. So it's going to be y plus 1. So this means the slope at any particular point when x is 1 or -1, the slope is going to be 1 more than the y value. Okay, so we'll do it at x equals 1 first, and then we'll just kind of copy that over to x equals -1. When y is 0, the slope is 0 plus 1, so the slope will be 1. When y is 0, the slope is 1, which means we're kind of aiming at this point. I wonder if we'll have the same sort of pattern here. When y is 1, we would have a slope of 1 plus 1, so a slope of 2. When y is 1, we'll be up at this particular point, and the slope is 2. And again, it's aiming at that point there. I think the same thing will happen up here at y equals 2. When y is 2, the derivative is 2 plus 1, which is 3. The slope is 3, so it's going to look like that. And we keep going like this. When y is -1, we'll have a slope of 0, -1 plus 1. And when y is -2, we'll have a slope of -1. We're going to copy these over to when x is -1. Okay. And then finally, when x is plus or minus 2, y prime will be plus or minus 2 quantity squared plus y. So, oh my goodness, y prime is going to be y plus 4. Okay, so our slopes are going to get very big. I'm going to get really sloppy. So when when x is 2, y is -2, I'll have a slope of 2. Well, the slope of 2 would kind of go from this point, x equals 2, y equals -2. I would go up 2 and over 1. So my slope is going to be kind of like that. Okay, that's a slope of 2. And then when y is -1, I'll have a slope of 3. Right? Because -1 plus 4 is 3, so it's getting steeper. And when y is 0, we have a slope of 4. I'm getting really sloppy here. These are going to look almost vertical here. The same thing will happen over here. I'll have a slope of 2, so I'm aiming at this particular point because I'm going to go up 2 and over 1. And then I'll have a slope of 3. I would go up 3 and over 1, so that's kind of a little bit steeper there. And then a slope of 4, 5, and 6 are almost vertical. Okay, so this is a little bit hard to see the pattern here, and I always struggle with this next part, but I manage. So I'm supposed to now add the particular solution when y of 0 is equal to 0. So what I'm going to do is I'm going to plot that point, and then I'm just going to move a little bit away from that point as I draw it. As I move to the left and as I move to the right, I need to think about what's happening in each case. Well, as I move to the left, the slopes are getting negative, right? As I move this way, the next point that I encounter, the slope is -1, and then the slope is, oh my goodness, I'm not -1, it's +1, and then it was what, 2 or 4 there? Ooh. Okay, so they're getting steep and positive as we move to the left there. So let me draw that. So I think I should be have positive slopes, and it should taper off something like this. Now this is very imprecise, but it might work for us. Okay, as I move off to the right, on the other hand, the slopes are getting positive, okay, and then they continue to get big. Okay, notice that right here, I'm kind of parallel to that particular dash, so it's going to look something like that. That may not be perfectly accurate, but it's a good representation. Okay, so what we're going to do to conclude this is I'm going to give us 6 different direction fields like we've been seeing. I'm going to look at 6 different direction fields, and we're going to match up which particular differential equation goes with which direction field. Here are some things that we can do in order to help us out. I think one of the easiest things to do is figure out when the derivative is 0. Along that particular line, or that curve, our dashes would be horizontal. So let's suppose that I get an equation x equals y squared. Along the curve x equals y squared, I would have horizontal dashes. Okay, find any straight line solutions in the direction field. Oh, like we did before. So draw a curve that is a straight line that would be a particular solution, and then see if you can trace your way back from there. Maybe you want to compare 2 direction fields. You say, hey, they have these characteristics in common, but here's a characteristic they differ in. So how will I determine which is which there? Find the slopes at particular values. So I might notice that in one of the direction fields I have positive slopes in the first quadrant, and in another direction field I have negative slopes, and that might help me figure out which is which. Find out when dashes are vertical. What would cause a dash to be vertical? Well, a vertical line has an undefined slope. Undefined slopes are often produced by having zeros in the denominator. And then maybe draw some particular solutions to help you out. Okay, so here are 7 differential equations and 6 direction fields. One of them is not going to be a direction field for us. I'm a big fan of setting it equal to 0 and going from there. So in part A, let's look at the differential equation A. I have y prime equals x plus y. Well, if I set y prime equal to 0, I get 0 equals x plus y. I like having things solved for y. Y equals negative x. So A, the direction field for A, we will have the derivative equal to 0 along this line. So I'm going to think about slopes, the equation y equals negative x, and look to see if the slopes are 0 there. So we'll just use our little pointer here. Is this a good candidate? Y equals negative x is this particular line. Along that line, are the slopes all equal to 0? I don't think so. In the second quadrant they're all positive. In the fourth quadrant, they're all negative. No, they're not all 0 there. How about here? This is a potential candidate. Is that true? Yeah, because let me go ahead and draw that line, since I'm a little bit curious about this one. You notice that down here we have a slope that's a little positive, then we have one that's a little bit negative. Here it's one that's positive and then negative. To go from positive to negative, we have to pass through 0. So that seems like a potential candidate for A. Maybe it's the only one. If that's it, then I know that that's A. Let's continue. The next one, no, same issue. I have negative slopes here. I have positive slopes there. That's not good. Ooh, here's one that might be a candidate. Oh, no, of course it's not. What am I saying? The slopes should be 0. Those slopes are pretty much -1 there, aren't they? That's interesting. Maybe we'll keep that in mind for later. Here's one that looks good, though. I have negative slope, a positive slope, a negative slope, a positive slope. I think this is another potential candidate for graph A there. And then the last one is definitely not A. It's not A because here the slopes are negative. Here they're also negative. So that's not going to work for part A either. Okay, so now we have to figure out which one A is. Is it this one or is it this one? Well, I'm going to go ahead and look at in the first quadrant. What do I notice about the first quadrant? For this particular function, all the slopes are negative in the first quadrant because those dashes are falling. In this one, they're all positive. That may be enough for me to figure this out. Think about y prime equals x plus a. I'm sorry, y prime equals x plus y. If I pick an ordered pair in the first quadrant, let's say we pick 1, 1, and plug in 1 and 1 for x and y, I would get 1 plus 1 or 2. I would get a positive number. So that means that this last one here must be a. So a is this graph down here. Okay, now I'm going to reverse engineer things. I know I have 6 direction fields, but I have 7 differential equations. So I'm going to see if there's another differential equation where when x is the opposite of y, I'll get 0. Well, in part B, if x is the opposite of y, I would have negative y minus y. That would be negative 2y. That doesn't work. If I've said x is the opposite of y, really y is the opposite of x. If y is negative x, I'd have x minus negative x or x plus x. That doesn't work. If y is negative x here, I'd have negative x minus x, which is negative 2x. Nope. If y is negative x, I have negative x minus negative x, or negative x plus x. So D must be this guy, because it's the only other one that has a slope, or has slopes of 0 along the line y equals negative x. So that's D. Okay, let's go from here. Let's go to part B. For equation B, I have y prime equals x minus y. If I set x minus y equal to 0, and I add y to both sides, I'll get y equals x. So along the line y equals x, we should have slopes that are equal to 0. Let's look at this guy. Along y equals x, oh, look at that. I've got positive slopes then negative slopes. Positive then negative. Positive, negative. So this one looks like a candidate for that one. Let's draw that line in. That's a good one. How about the third one in here? Hey, look at that. Once again, along this line, I have negative slopes and positive. Negatives, positive, negatives, positive, negatives, positive. Okay, so there's another one that's a candidate for B. Let's hope those are the only two. For the fourth one here, along the line y equals x, it looks like those slopes are about 1. They seem to match that particular one, so that's not a good one. And then over here, the slopes are positive. Here the slopes are positive. No, that doesn't seem to match. So either the first one or the third one is going to be B. And we've already eliminated D, so let's highlight that one because it's gone. Okay? So we can do a similar trick to figure out which one is B in terms of looking at quadrants. In the fourth quadrant, I notice that the slopes are negative for the first graph, and here they're positive. So let's pick an ordered pair. Let's pick the ordered pair, well, that's 2.5, negative 2.5. If I substitute x equals 2.5 into x minus y, I get 2.5 minus negative 2.5, which is the y value, which is positive 5. Well, the slopes here are negative. That doesn't work. However, over here at 2.5, negative 2.5, the slopes are positive. So it looks like this must be B. Okay? So when y and x were equal, we ended up with all 0 slopes. Okay, so now we know where B is. Now it's time to look for part C. Okay, part C, we have y minus x. If y is equal to x, we'd have x minus x, which is 0. So here's the other one. So this must be part C here. If you want, you could verify it by substituting in some of those values. in each quadrant and seeing that the slopes signs agree. So now we're down to E, F, and G, and it's just these last two graphs. Okay, so I'm going to think about E. E is x divided by y. If x is 0, that means we're on the y-axis. On the y-axis, we would have 0 divided by y, which would be 0. Along the y-axis, do I have slopes of 0? I do. Oh, that's interesting. So that could be E. Let's check out the other one. Along the y-axis, do I have slopes of 0? Oh, so that could be E as well. Okay, so E is either this one or this one. That didn't help me. It might not be either. Okay, let's look at F. I've already made the observation that when x is equal to 0, we get horizontal slopes. The derivative is 0. So let's look at F. F is y divided by x. If x is 0, we're dividing by 0, so we should have vertical slopes there. We don't have that. So F is the bad guy. He's the one that doesn't belong at all. So we rule him out. So now we just need to decide which is F and which is G. Let's go, or which is E and which is G. So let's go back to this guy, E. Here I'm taking x and I'm dividing it by y. Since we just discussed this for part F, if I divide by 0, I should end up with vertical lines, vertical dashes. So that would be when y is 0. That means on the x-axis. On the x-axis, does it appear we have vertical lines? Okay, they're not drawn there, but let's check this out. Well, let's look over here in this region. Here they're very steep and negative, very steep and positive. Hey, look at that. I think they would be straight up and down there. This is looking a lot like it's part E. Over here, on the other hand, notice what they're doing. Here, it's very steep and negative way up here, but it's getting less steep. And I think by the time we reach the x-axis, it's going to be flat. Okay? So that would mean that when y is 0, the derivative will be 0. Oh, that agrees with G. So this one, this last one must be G, and this guy must be E.